We built these mirrors to look back in time. The James Webb Space Telescope is catching light traveling for over 13 billion years, showing us the universe when it was barely an infant. But when we look at that ancient light, we see something that contradicts our current models. Webb is finding massive, fully formed galaxies and gigantic supermassive black holes, existing just a few 100 million years after the Big Bang. Standard cosmology tells us this timeline doesn't work. To build a supermassive black hole, clouds of gas have to collapse, ignite into stars, live out their lives, die, and merge. That process takes billions of years. Yet we are seeing these giant structures fully formed at the dawn of time. This animated grid represents coordinate time, the core assumption we use in modern astrophysics. When we simulate the cosmos, we assume the entire universe operates on a single, synchronized global clock. Every second ticks exactly the same everywhere. If every ticking second is the same everywhere, then gravity only has so much time to work. As we watch these particles drift across the grid, they simply run out of time to clump together and build the giant structures Webb is seeing. The early universe appears to be breaking its own speed limit. To solve this crisis, we have to dismantle our assumption of a universal clock. A century ago, Albert Einstein proved that time is flexible. Under general relativity, intense gravity physically dictates the speed of time. During the violent expansion of the early universe, regions of extreme density collapsed. These localized pockets were violently forged into primordial black holes. This animated diagram illustrates the core mechanism of structural cosmology. As loose matter approaches these primordial seeds, it falls into a deep gravitational well. The closer it gets, the more its local clock slows down relative to the universe. Replacing one universal clock with localized pockets of altered time creates a theoretical loophole. Matter behaves differently when it is running on its own slowed-down schedule. To test this temporal trap, I wrote an n-body simulation in Python. The standard model, on the left, shares a global clock, so particles scatter. The structural cosmology model uses local proper time. Slowed clocks, in yellow, force particles to rapidly cluster around the seeds. By slowing time down on a local level, we paradoxically accelerate the density of structure formation. This difference bridges the gap, allowing giant galaxies to form within the short window Webb observed. If this mechanism is responsible for early cosmic structure, then primordial black holes must account for 10 to 30% of the dark matter in modern galactic halos. This isn't presented as a certainty, but as a testable framework that includes specific conditions for its own destruction. This chart plots our upcoming observation targets. Over its operational lifetime, the Nancy Grace Roman Space Telescope will look for Earth mass microlensing events, moments where a small black hole magnifies the light of a background star. To prove this hypothesis, the survey must detect between 30 and 100 of these events. At the same time, the Vera C. Rubin Observatory must detect 50 to 200 solar mass microlensing events, and they must be distributed in a spherical halo around the galaxy. If these telescopes complete their surveys by 2035 and find fewer events, or if the spatial distribution is a flat disk rather than a halo, the structural cosmology model is dead, falsified. There is a deep joy in taking an idea, coding a simulation to watch it play out, and then throwing it against raw observational reality to see if it survives. Whether these simulations correctly identify the variable we've been missing or are discarded as a mistake, we have turned the nature of cosmic time into a testable measurement. It allows us to stop assuming how time behaves and start verifying it.